What if the key to understanding life, disease, and the universe itself lies hidden in something so small you can't even see it? Imagine building machines so small they can travel through your bloodstream, repair tissue, or assemble materials atom by atom. Imagine, too, that every breath you exhale carries invisible chemical clues that can reveal diseases long before symptoms appear. These breakthroughs sound like science fiction, but they're not. Everything in these technologies starts with atoms. But here's the real question. How can something so tiny hold the secrets of matter? And when did humans first begin to understand it? The search to understand what matter is made of began long before modern science, more than 2,000 years ago in ancient Greece. In the 5th century BCE, philosophers Leucippus and Democritus proposed a radical idea. They argued that if you kept dividing a piece of matter eventually, you would reach a point where it could no longer be divided. They called these smallest pieces atomos, meaning indivisible. To them, atoms were invisible particles moving through empty space and combining in countless ways to form all substances. It was an idea conceived not through experimentation, but through logical reasoning and imagination, a philosophical attempt to explain the diversity of the material world, but not everyone agreed. Influential philosophers like Aristotle and Plato rejected the atomic theory. Instead, they believed that everything was made from 4 fundamental elements: earth, air, fire, and water, and that matter could be divided infinitely. Because experimentation wasn't part of Greek philosophy, Aristotle's view dominated for nearly 2,000 years. Can you imagine how different science might have been if Democritus's idea had been accepted? That's a question history will never answer. As the Renaissance dawned in Europe, a new approach to truth emerged: observation and experimentation. Thinkers like Copernicus, Francis Bacon, Robert Boyle, Galileo Galilei, Johannes Kepler, and Isaac Newton challenged the old ways. They asked, what if we tested ideas instead of accepting them? This shift laid the groundwork for the man who would transform chemistry forever: John Dalton. In the early 19th century, John Dalton, an English teacher and chemist, resurrected the ancient atomic idea and gave it experimental proof. In 1808, he proposed his atomic theory, built on 4 revolutionary postulates. 1. All matter is composed of tiny, indivisible atoms. 2. All atoms of the same element are identical in mass and properties, but different from those of other elements. 3. Atoms combine in simple, whole number ratios to form compounds. 4. In chemical reactions, atoms are neither created nor destroyed, only rearranged. Dalton didn't just speculate, he measured, observed, and built his theory upon evidence. But how did he know atoms combined in simple ratios? The answer lies in a series of fundamental chemical laws discovered just before his time. Before Dalton, the French chemist Antoine Lavoisier had made a groundbreaking discovery: matter cannot be created or destroyed. In every chemical reaction, the total mass of what you start with equals the total mass of what you end with. Mass is neither created nor destroyed in a chemical reaction. For example, when sodium reacts with chlorine to form table salt, the combined mass of both elements is exactly equal to the mass of the salt produced. This meant that atoms were not disappearing, only rearranging, a cornerstone of Dalton's later work. But that was just the beginning. Soon after, Joseph Proust noticed something astonishing. No matter where a compound came from, it always contained the same elements in the same fixed proportions by mass. A compound always has the same ratio by mass of its constituent elements. Water, for example, always breaks down into 8 parts oxygen and 1 part hydrogen by mass. Ammonia always contains nitrogen and hydrogen in a 4.7:1 ratio. These consistent numbers could only mean one thing: matter is made up of atoms combining in specific fixed ratios. But Dalton saw something even deeper. Dalton realized that when 2 elements form more than one compound, the ratios of their masses follow simple whole numbers. Take carbon and oxygen. They form carbon monoxide, CO, and carbon dioxide, CO2. In carbon monoxide, 1 gram of carbon combines with 1.33 grams of oxygen. In carbon dioxide, that same carbon combines with 2.67 grams of oxygen. The ratio between them, 2 to 1, revealed that carbon dioxide has twice as many oxygen atoms per carbon atom as carbon monoxide. These simple whole number ratios could only happen if matter was built from discrete, countable particles, atoms. We've learned that elements can combine in fixed or multiple ratios by mass, giving rise to two important laws: the law of definite proportions and the law of multiple proportions. But how can we tell which law applies to a given set of data? Let's look at an example to find out. This question asks you to decide whether the data for two compounds, A and B, show the law of definite proportions, the law of multiple proportions, or neither. The law of definite proportions says that a specific compound always contains the same elements in exactly the same ratio by mass. The law of multiple proportions says that when the same two elements form more than one compound, the ratios of the masses of one element that combine with a fixed mass of the other are simple whole numbers. In this problem, both compounds contain carbon and oxygen, but in different amounts. You need to compare how much oxygen combines with a fixed amount of carbon in each compound to see if the ratio forms a simple whole number. In this case, both compounds, A and B, contain carbon and oxygen. In compound A, the mass ratio of oxygen to carbon is 1.33 to 1. In compound B, the ratio is 2.67 to 1. The ratio between these two values is 2 to 1, a simple whole number. Therefore, these data show the law of multiple proportions. This means that A and B are different compounds made of the same elements combined in different proportions. The law of conservation of mass, the law of definite proportions, and the law of multiple proportions formed the experimental backbone of Dalton's atomic theory. Even though we now know that atoms can be split into smaller subatomic particles and isotopes vary in mass, Dalton's ideas changed everything. He, along with other pioneering scientists, turned chemistry from a mysterious practice into a precise quantitative science that could predict the behavior of matter. All of this shows that the atoms around us are more than just tiny building blocks. They carry a history and future. So remember, the very atoms in your breath once journeyed through stars, oceans, and the lives of ancient civilizations. And these same atoms will shape the technologies of the future, from nanomachines in our bodies to materials we have yet to imagine. Enjoyed this video? Like, subscribe, and hit the bell for more chemistry content. Until next time, stay curious and keep exploring.